recall that any polynomial on R is continuous. We prove this by first proving that X is continuous, and then we applied induction and the algebraic theorems for limits and continuity to show that sums of continuous functions is continuous, products of continuous functions is continuous, and then applied induction to show that any polynomial is a continuous function. Let's try to prove this directly for one candidate polynomial, which we have already done once. Let's go through that proof carefully again. Consider the function x squared. Suppose you want to show that this is continuous. Well, observe that for fixed x naught, x squared minus x naught squared modulus is less than or equal to, or rather it's just equal to, mod x naught plus x times x minus x naught. Right? Now we can assume that mod x minus x naught is less than 1. Why can we make this assumption? Ultimately, we are going to fix epsilon and find a delta. May as well choose delta to be some quantity that is less than 1 also. Now fix epsilon greater than 0. Fix epsilon greater than 0. Well, from the fact that mod x minus x naught is less than 1, we immediately get that mod x is less than 1 plus mod x naught. Right? So this whole thing is going to be less than 1 plus mod x naught times mod x minus x naught. Okay? Now, if mod x minus x naught is less than epsilon by 1 plus mod x naught, then we get mod x squared minus x naught squared is less than epsilon. Right? So our choice of delta corresponding to epsilon is minimum of 1 comma epsilon by 1 plus mod x naught. Right? We have found a delta in terms of epsilon. In other words, not only have I shown continuity, I have given you a recipe that for any point x naught, you give me the epsilon, I will return for your delta value, which you can compute by a very simple expression that will satisfy the epsilon delta definition of continuity. Right? Observe that delta depends not only on epsilon but also on the point x naught. Note, I am not saying that it is impossible to find a delta that works in the definition of epsilon delta which is independent of x naught. That's not what I'm saying. It might be possible. We have to show that such a choice is impossible. That we will do later on. But as things stand, our current algorithm or recipe for choosing delta is very much dependent on the choice of x naught. So this function x squared is continuous, but its behavior at various points with respect to the epsilon delta definition will change depending on the point. If x naught is very large, then our algorithm is going to return a delta which is much smaller than epsilon. As you can see, if x naught is 10,000, delta will be epsilon by 10,001. So the function x squared, as you start going further away from the origin towards infinity, sort of increases rapidly. That's what this is capturing. Now, this discussion motivates the following definition. Let f from set A to R be a function that is continuous. We say f is uniformly continuous if for each x in A there exists the epsilon delta definition for continuity can be satisfied with the choice of delta that is independent of the choice of x. So first of all, at each point of x, the definition of epsilon delta should be satisfied, but the choice of delta does not depend on the choice of point. It is just a function of epsilon. So let's write this. This definition was given in English. It might be prone to misinterpretation. So let's write it in logical notation to fully understand without any imprecision what is going on. Well, what does the epsilon delta definition say? For all x in A, there exists delta. So first let's write for all epsilon. Let's write it properly. It says for all x in A, for all epsilon greater than 0, there exists delta greater than 0 such that mod f of x minus f of y is less than epsilon whenever mod x minus y is less than epsilon. This is the usual definition of continuity. What it says is, for each point x in A and for each choice of epsilon greater than 0, there is a delta greater than 0 such that something happens. Okay. Now, this is the definition of continuity. A slight twist would give you the definition of uniform continuity. The choice of delta should be independent of x. So what you do is, for each epsilon greater than 0, there exists delta greater than 0 for all x in A. Note what has happened. You fix an epsilon, there is a corresponding delta greater than 0 such that for all x in A, if mod x minus y is less than epsilon, then mod f of x minus f of y is, if it's less than delta, here also I made the same mistake, delta here is less than epsilon, right? So this captures uniform continuity. What this says is that the choice of delta depends only on the choice of epsilon, and the choice of point is not into the picture at all. Okay. Now, are there uniform continuous functions at all? Well, examples. Number one, the function f of x equal to x is uniformly continuous. Well, this is very obvious because here you can choose delta to be just epsilon, right? You don't need to do anything complicated or sophisticated here. Number 2, the function x squared from R to R is not uniformly continuous. Well, is this clear? We just saw this, right? No, as I remarked there, we have not asserted that it is impossible to find a delta that is independent of the choice of point. It just so happens that our recipe for doing that depends crucially on the choice of point x0. Now we have to make, or rather prove, that it is impossible to choose delta that is independent of the choice of point x0. Let's prove that. Let us prove this. Okay. Now, how can a function fail to be uniformly continuous? Let's try to understand this before we proceed to prove that x squared from R to R is not uniformly continuous. For that, let's look at the logical version of uniform continuity. For each epsilon greater than 0, there x is delta greater than 0 for all x in A such that something happens. What is the negation of this? Well, we are now experts at negating. The negation of this is, let me negate it here. There exists epsilon greater than 0 such that for all delta greater than 0, there exists x in A such that mod x minus y is less than delta, but mod f of x minus f of y is greater than or equal to epsilon, right? What is this saying? The only way by which the definition of uniform continuity can fail is if there is some epsilon that plays spoil sport. So there exists an epsilon greater than 0. How will it play a spoil sport? No matter what delta you choose, the definition of uniform continuity cannot be satisfied. That means for each choice of delta, there must be some point x that plays spoil sport. And what is the meaning of play spoil sport? Well, x is close to y, but nevertheless f of x and f of y cannot be made closer than epsilon. Okay, so this is the negation of uniform continuity. Okay, how does this help us to show that x squared is not uniformly continuous? Well, choose epsilon equal to 1. What we are going to do is, for each delta greater than 0, we are going to show that there are points x comma y in R such that mod x minus y is less than delta, but x squared minus y squared is greater than or equal to 1. Okay, now what you do is choose x equal to 1 by delta. Choose x equal to 1 by delta and y equal to x plus delta by 2, right? X plus delta by 2. Now certainly mod x minus y is less than delta. In fact, it's exactly equal to delta by 2. Okay, then note that mod x squared minus y squared is in fact equal to just 1 by delta squared minus 1 by delta plus delta by 2 the whole square. right? This is just 1 by delta plus delta by 2 plus 1 by delta. I'm just writing mod x plus y into mod x minus y in a weird way, okay? Into delta by 2, modulus of delta by 2, right? So you will get modulus of 2 by delta plus delta by 2 into mod delta by 2, right? Right? So when you multiply this out, it's clear that you get some quantity which is strictly greater than 1, right? In fact, what you get is modulus of 1 plus delta squared by 4, which is strictly greater than 1. So we have contradicted the definition of uniform continuity. Hence, x squared is not uniformly continuous. Not uniformly continuous. This example should make this proposition obvious, and I'm going to leave it to you to prove it. Let f from a to r be a function, then f is not uniformly continuous, if and only if we can find sequences xn comma yn in A with xn minus yn converging to 0 such that for some epsilon greater than 0 mod f of xn minus f of yn is greater than or equal to epsilon. You can find two sequences that get arbitrarily close to each other, which is captured by saying xn minus yn converges to 0, but nevertheless mod fxn minus fyn is always somewhat far away, at least epsilon distance away. Okay, so we have seen example of a non-uniformly continuous function. This example sort of says that if you want to find a candidate point that allows you to defeat the epsilon delta definition for uniform continuity, you may have to go very far away. If delta is we have fixed epsilon equal to 1. If delta is very small, then 1 by delta is very large. So to defeat the definition of uniform continuity, you have to show that no delta works for some choice of epsilon, and you may have to go very far away. This might suggest that if you have a function defined on R, but you restrict it to some bounded piece, then the function is indeed going to be uniformly continuous, because you cannot arbitrarily choose points larger and larger away if you are confined within a bounded area. You should be thinking of the adjective compact and why it is called compact right now. Theorem. Any continuous function f from k to r where k is compact is uniformly continuous. Why? Well, we have to prove it. Now you can prove this in several ways. I am going to prove it using open covers and finite subcovers. Okay. Suppose epsilon greater than 0 is given to you. I have to find a delta greater than 0 that is independent of the point x in k but depends only on epsilon, such that the epsilon delta definition is satisfied for every point in the set k. Okay, now observe that for each x in k we can find delta greater than 0 that satisfies the epsilon delta definition, right? That's because the function is given to be continuous. In other words, what I will do is I will first change this notation slightly. I will make this delta x. In other words, f of b x delta x is contained in b fx epsilon. This is just the topological way of stating the epsilon delta definition, one of the equivalent ways of saying that a function f is continuous. Okay, now look at the collection O, which is defined to be b x delta x as x runs through k. O is obviously an open cover of k, right? So one mistake I have made, to be ultra precise, I cannot just take f of this. I have to do b x delta x intersect k, right? That otherwise it doesn't make sense. Let me make one more change, a slight tweak to the epsilon delta definition here to make the rest of the proof flow more smoothly. What I will do is I will not just require b of x comma delta x intersect k f of that to be in b of f of x epsilon. What I will do is I will first put a by 2 here. So that means I'll make it epsilon by 2. And here I will make it 2 delta x. So all I have done is the epsilon delta definition is anyway satisfied. I have just adjusted my quantities so that b of x comma 2 delta x intersect k is contained in b of f of x epsilon by 2. This can always be done. Think about why if you're not sure. Okay. Now we know that this b of x delta x is an open cover. By compactness, we can find finitely many elements in K such that, for ease of notation, I'm going to simplify the subscripts such that b of x1 delta 1 union b of x n delta n, this covers K. Technically I should be writing delta x1 delta x2 so on. That's a bit cumbersome. I'm just simplifying the notation. This is just by compactness. Now choose delta to be the minimum of these delta 1 to delta n. Okay, claim is that this delta works in the definition of uniform continuity. Okay, let's see why this is the case. So fix x in K. Aim is to show f of b of x delta intersect K is a subset of b of f of x epsilon, right? This is our aim. Then we would be done. Well, since x is in K, we can find some xi, say x1, such that x is an element of b x1 delta, or sorry, b x1 delta 1. So these b xi delta I is union of that is k, so any element x will have to be in one of them. I am just taking for concreteness that particular element to be x1 delta 1. Okay. Now this just means mod x minus x1 is less than delta 1. Okay. But b of x delta will therefore be contained in b of x1 to delta 1. This is because delta is less than or equal to delta 1. This is because delta will be less than or equal to delta 1. If you want to see a proof of this, let me just do it once, because I am going to pull a similar trick soon. So if y is in bx delta, then mod y minus x1 is less than or equal to mod y minus x plus mod x minus x1. This quantity is already less than delta 1. This quantity is already less than delta 1, and mod y minus x is less than delta, and delta is less than or equal to delta 1, and we get this. This is just a simple application of the triangle inequality. Okay. What does this give us? That gives us that f of b x1 comma 2 delta 1 is contained in b f of x1 comma epsilon by 2. Okay. Why is that? Well, you can see that here. We had chosen with these additional constants that I added on later, a factor of 2 on the left and a divider by 2 on the right, precisely for this reason. Okay. You will get f of b of x1 2 delta 1 is contained in b of f of x1 epsilon by 2. In fact, you will get f of b of x delta is contained in this. Okay. To be ultra accurate, I must again make this minor change. F of b of x delta intersect k is subset of f of b x1 2 delta 1 intersect k is contained in b of f of x1 epsilon by 2. Okay. How does this solve the problem for us? Well, f of x is obviously there as an element of b of f of x1 comma epsilon by 2. Right? F of x is certainly going to be an element of this. Well, by simple logic, we see now that this thing is going to be contained in b of f of x epsilon. Why? Well, it will be easy. We have already seen a similar argument. Okay. So what have we got? We have got f of b of x delta intersect k is a subset of b of f of x epsilon. Haha, we are done. So this was a somewhat technical proof, fiddling around with the quantities to make everything work, but it's just a straightforward application of the open cover form of compactness. So we have now shown that a continuous function on a compact set is uniformly continuous. The question now arises, though this concept of uniform continuity seems natural in the light that we were interested in when the function, when the delta is a function of epsilon alone and does not depend on the choice of point. That's an interesting theoretical question. But is it of any value? Well, look through the exercises or stay tuned for the chapter on integration where we see a deeper application. This is a course on real analysis and you have just watched the module on uniform continuity.